range. What are they? Well, domain talks about what x values that you're allowed to use in your equation, and range just talks about the y values that are used in your equation. So let's talk about domain and range in these two examples. The first one you're going to notice is a bunch of dots. We call that a discrete type of data. So discrete refers to individual distinct dots, versus on the right-hand side, you're going to see that we have a smooth connected line. We refer to that as a continuous relationship. So there's no breaks in it. It's just all nice and smooth and connected. When we're talking about discrete data, those are very distinct points. So we can see exactly what x values are used in the data. I could even go through and list all of the ordered pairs. Like for example, this first one here would be the ordered pair 0, 1. And then moving just along the right, I've got 1, 3, 2, 2, 4, 4, and 5, 4. So there are 5 points in this relationship, and I've listed all 5 ordered pairs. To then go look at the domain of this relation, all I'm going to do is list the x values that we use, because there's only 5 of them. There's no more, no less, there's only 5. So I can just tell you exactly what those 5 are. I put it in a little curly brace like this, and that just says, hey, here's a list of numbers. And then I just list all those x values, 0, 1, 2, 4, and 5. For my range, I go through and I look at the y values that I have. So my range, again, I'm just looking at my ordered pairs. I see 1. I would like to put them in order, so I go 1, and then I see 3 is next, and then 2, but I'll go 1, 2, 3, 4. And then if you notice, I have a y value of 4 in 2 different places. So technically, I have 4 and 4. But if I were to write the second 4 in this list, I'm basically telling you, hey, you can use the numbers 1, 2, 3, 4, and 4. But I already told you can use 4. So I don't need to tell you a second time that you're allowed to use the value 4. So I only need to write it one time when I'm listing out my range, and this would be my domain and my range for that discrete relation. Now, looking over at the right, we'll talk about the continuous data. Now for continuous, there are so many points connecting each of the 2 dots that I'm never going to be able to list them all out. I have a point, for example, here, 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 here. There's millions and millions, actually an infinite number of points along that pink curve that I have. So what I'm going to do instead is say, starting and ending on my continuous curve, I can use any number in between. There's nothing off limits as long as you're between the beginning and the end. So for my domain, I am going to look at my x values, and I'm going to say where do they start and where do they end. And then x can be anything in between those 2 numbers. So let's first start with where they end. So when I look at my x's, I see that my graph ends at 5. So any x value that I use has to be less than or equal to 5. And I know we can be equal to because I actually have a dot right here on 5. So I know that 5 is allowed. So I go ahead and say, okay, well, x has to be less than or equal to 5. Perfect. So that's one boundary. But we can't go less than or equal to 5 forever, because that's numbers like 4, 3, 2, 1, 0, -1, -2. And my pink curve doesn't hit 0 or -1 or -2. My pink curve actually stops here. That's as far left as I'm allowed to go. So the farthest left that I'm allowed to go is +1. And that gives us our lower boundary. So in this inequality that I'm writing, I'm going to sandwich the x between the 5 on the higher end, and then on the lower end, I'm also going to write that it has to be greater than or equal to 1. So I have 2 conditions sandwiched into one inequality. That x has to be greater than or equal to 1, but it also has to be less than or equal to 5. So what I've done is I've said I'm allowed to use x values that start here and end here. Now we're going to do the same thing with your range, your y values. So my range is going to look very similar, except we're talking about y's, and y's go from bottom to top. So I'm going to start this time with the bottom boundary, and then I'll go up to the top. So looking at the lowest my graph goes, I see that the lowest it goes is 2. And then the highest we go is up here to 4. Now I have a dot on 2 and a dot on 4, so I am allowed to use both of those numbers. So when I go put my endpoints in, I'm going to make sure that they're using greater than or equal to and less than or equal to signs. So my y needs to be greater than or equal to. It has to be above the smallest value, which is 2. So 2 is my lower bound, and then my y has to be less than or equal to, it has to be below the upper bound, which, if I look at kind of the ceiling or the top of my graph, is at 4. And I'm allowed to use any number in between as long as it's bigger than 2 and less than 4. So I could have 2, 2 and a quarter, 2 and a half, 2.9, 2.97, 3, 3.01, any number. And that's why we don't list them, because there's so many, you're never, ever, ever going to get to them all. So for continuous data, you'll use probably an inequality statement like this. There may be another way that your teacher has you represent it, but this is one of a couple options. For discrete data, for the dots, you're just going to go through and list all of the x values and list all of the y values that you use. So hope that helped. Thanks for watching, and I'll see you next time. Bye.